All right. The last items I'm going to look at in this unit is group trends. And so these are just some things that we see about the families that you need to know. All right. The first group, 1, and in some books it's 1A, are the alkaline earth metal. The alkali metals. The alkali metals, you need to know its name. They're in that group. If you take a look at them, all of them have one extra electron past the noble gas, and so their reactivity is to lose that one s electron. The reactivity is, as you go down, they become more reactive. This is because the ionization energy is lower as you go down that group. Because the electrons are further away, it's easier to steal. Easier to steal the electron, that's its reactivity. We will learn this later, but if you react a metal that is an alkali metal with water, it forms a metal, that's what the M is, and a hydroxide. That is the OH minus ion. And it also forms hydrogen gas, which is explosive. And when you form hydroxides, you make heat. And so if you have an explosive gas with heat, they tend to explode. And you can see this spectacularly if you've reacted an alkali metal. And so, stop. Okay, so I'm going to show you what that looks like. Now, as it goes from right to left, they get more reactive. Okay, so it'll go that way. All right, alkali metals also have a tendency for something that is really kind of spectacular. If you take a solution and you take and wet a metal with that solution and you put it in a flame, the color that is given off represents the transitions from the S electrons into the P and then back down. They give off distinct colors. And so a yellow line comes from sodium, a red line comes from lithium, a potassium gives a purple color. Quite often the colors from fireworks are the inclusion of these particular metals, and when they explode and burn, that's what gives the color. White is magnesium, which is in the next group, but we can see distinct colors when these particular metals are heated, and the electrons get excited, and then they go back to the ground state, and they give off particular wavelengths of energy. Hydrogen is an alkali metal, but hydrogen is in itself its own special case. It's really unique. It has 1 electron, 1 proton. It is found as what's called a diatomic gas, di meaning 2 atoms. In its molecular form, 2 of them are bound together. Hydrogen, when it reacts, can either gain 1 electron, become negative, or lose 1 electron, become positive. This is very rare for elements to go either way. It can form an anion and a cation. And when we look at chemistry of the hydrogen in chemistry that is general chemistry, most of the things that we do are in water. And so the type of reactions that you see hydrogen do most often in our class is it becoming a positive charge, a H plus proton. We'll deal with hydrogen very, very often. The alkaline earth metals, similar to the alkali metals. Their reactions are dominated because they have 2 electrons more than the noble gas, so they become a +2. Their reactivity, as you move down, becomes more reactive. And they react with water the same way, making metal hydroxides and hydrogen gas. They're just not as exciting as the alkali metals. They have higher densities than the and melting points than the alkali metals, a little bit heavier. They melt a little bit more at higher temperatures, and they have lower ionization energies. That means they're less reactive. So those are those first 2 groups. The oxygen group is very important to us. Oxygen itself is really an important molecule. There are 2 forms that are found naturally. The one that we are very dependent upon O2 oxygen. That's what we breathe in. That's what we can use to do metabolism. But there's also a form called ozone, O3. The elemental form is O2. Ozone is a compound that is created high in the atmosphere. Ozone is pungent and toxic. It's actually used to purify water. The ozone layer protects us, though, from UV radiation outside. Sulfur is interesting. It reacts like oxygen, but it is found as S8 in nature. It is 8 sulfurs put together, and that is the elemental form. The reactivity that we have for this group is that it gains 2 electrons. We, in that group, have some nonmetals, have some metalloids, and some metals as you go down, so we have a representative of each of those groups. The 2, and this is a terminology, allotrope. Okay, an allotrope is this. It is the form of an element, okay, that has different combinations of numbers. And so an allotrope of oxygen, we find it normally as O2, but the second allotrope is O3, okay. It can form ions. It likes to accept electrons. It's very electronegative. And oxygen likes to form 2 negatives. That's just normal. But we have some oddball reactivities where we have a peroxide and a superoxide form. They happen rarely, but we do know that they exist. But they love to take electrons. If you have to predict it with no other piece of information, it should gain 2 electrons. That's what you predict. Because it's 8, it wants to become 10. I would have to give you more information if it forms one of the other ions. Here's what sulfur looks like, kind of like a crown, and that's its elemental form. And so most elements on the periodic table are just one element by itself, and that's how we represent it. But there are a few that are together. We're going to find 7 diatomics, and I'll show you those in a minute. And then sulfur is an oddball. When you write sulfur, the elemental form, it's S8. Halogens. That what we would see on our row up there is number 17. On other periodic tables, it's called group 7A. The halogens are really the most reactive nonmetals on the periodic table. Fluorine is known as the most reactive substance. Most of them are found as diatomic molecules. So fluorine is found as F2, fluorine is found as Cl2 in the elemental form. When they react with hydrogen, they all form strong acids, with the exception of HF. Fluorine is so reactive, we don't have fluorine gas in the building. Okay? Fluorine can diffuse through lots of things, including your hand, your skin. Fluorine loves to react with calcium. And so if a fluorine leak happens, it can diffuse through your hand and eat away the bone in your hand at that time. The only treatment that we have is to inject you with more calcium ions so that it reacts. It is not something we like to use because it is so reactive. Halogens. Okay, and if you think about the nonmetals, I said metals become reactive as I go down, as I go from right to left. They get more reactive. Nonmetals are the exact opposite because what they're doing is they're gaining electrons. So their reactivity, as you go from left to right, they become more reactive, and as they go from bottom to top, they become more reactive. Metals and nonmetals are opposites in all characteristics. And so they tend to be, halogens have very large electron affinities, meaning that they become stable if they gain an electron, so they react very well. Metals tend to give up electrons. Nonmetals want to gain electrons, so when a metal and a nonmetal get together, it's great. We form metal halides, what we call them. And something unique about chlorine, if we dissolve that in water, it creates a solution that is disinfectant. So your Clorox bleach. Bleach is a solution of the chlorine gas that has reacted with the water. Noble gases. Happiest elements on the periodic table. They're at Disneyland. They don't like to gain electrons because they have core electrons. I would have to promote that electron up into another level. They don't like to lose electrons because they have the perfect number, and so they don't react. Their ionization energies are huge, and they really have very little electron affinities. They just don't want to react, and so they are inert. Now, does that mean they can't react? Well, this is what we've done. We've taken some very large noble gases and reacted it with the most reactive thing. So this is a laboratory that is really, kind of dangerous. They want to react something that it's not supposed to react. We have made a few compounds with noble gases, with fluorine, not very many of them. They are oddballs. And they're interesting in that they violate some rules, and they show us some ways in which the metals or the atoms can bond in different ways that are possible. And so we'll look at that later, but there are just very, very, very few compounds ever reacted with noble gases. And these are about all of them that we know at this moment in time. Transition metals themselves, all we know is that when we deal with a transition metal, they are weird, right? They don't follow the trends perfectly. They don't do everything the way they're supposed to do. So when you deal with a transition metal, you have to give it a little bit more information. We have to really look at it. You might have to look up some reference material about a transition metal to know what's happening. Now, they tend to react by making cations. They give up electrons, but they're much less reactive than the alkali and the alkaline earth. So it takes more to react them. Many can form multiple charges because sometimes d electrons can get in the mix. We tend not to say that they d electrons react, but in real life, sometimes they do react. The lanthanide and the actinide block, those ones that we put on the bottom, we don't just put them on the bottom because they are unimportant. Why in the world we put them on the bottom is to make it print on an 8.5 by 11 sheet of piece of paper better. The lanthanides, those 14 elements, actually have, they act like metals. They are metals. They react to group about the same as the alkaline earth metals. They are rare, and there's a lot of variability in those. The actinides, on the other hand, most of them are man-made. The ones that do exist are all radioactive, and so that's the characteristics for them. Remember, the periodic table looks more like this in real life than it does in the way that you normally see it. Those actually fit between the gaps so that, and this is called the long form. You will only see the long form every so often. Okay. Oops. Chapter 5. Okay, Chapter 5. If you printed out the notes from the Moodle, I didn't like how they organized them. So I went ahead and redid the notes, and I'm going to give you these because I ordered them in an entirely different way. I will upload them eventually electronically once I'm happy with everything. But this is, I'm happy with what I'm doing. All right, what we're going to do is in this chapter, got an extra one? Yes. Hold on to it. In this chapter, what we're going to do is talk about chemical bonds. Okay. What is a chemical bond? Bond. James Bond. What's a bond? You don't know what a bond is? Connection between two atoms. You've got two atoms, and they're connected in some way. Okay? But there are several ways we can connect bonds together. And so we're going to describe a couple of those. All right. Ultimately, chemistry is rearranging bonds of molecules or creating new bonds between atoms. Now, the bonds that are happening and chemistry is essentially changing electrons. All right? And really what we're going to do, the electrons that are available for us to react are the valence electrons. That's why we went through the whole thing of showing you electron configuration, is to identify which are the electrons on the outside of the atoms that have the possibility, when you mix things together, those electrons are going to be involved in forming bonds and forming the connections between atoms. And so that's why we went through electron configuration. Now, we will eventually then show you and describe, not in this unit, but in the next unit, the three-dimensional arrangement that they have in space, because 3 dimensions is very important to know what's happening. 3-dimensional structures of molecules are so important, especially when you talk about something like a drug. A drug can be made, and you connect atoms together, and you can take the same atoms and connect them together, but one is left-handed and one is right-handed. One of those drugs could actually cause an effect that is beneficial, and the other version, because of its 3-dimensional space, can cause a side effect. And so knowing how these are 3-dimensionally arranged talks about how they behave in real life. And so we go from writing something on a flat piece of paper, making notations, to thinking about what does this molecule really look like in 3-dimensional space. Now, if we are going to look at reactions between two atoms, then we have to identify which electrons are available, and we use Lewis symbols to identify the valence electrons. And so you may have heard something called the octet rule. Have you heard that in high school? Octet means what number? 8. 8 is a very stable number, and that means 2s and 6p electrons creates a full shell, or the electron configuration of one of the noble gases. And so we have 8 electrons. Now, we consider the valence electrons only the s and p because most of the time only s and p react. And so if I do a Lewis symbol, okay, I take the symbol itself, X, depending upon how many s and p electrons, I would put the first one here at the top, the second one, the third one, the fourth one. Then I double up 5th, 6th, 7th, and 8th when I draw Lewis symbols. 8 electrons around an atom fulfills its octet, fulfills its stability, and if you have to predict, 8 around is what is stable. There are ways to make an exception, but you'll have to calculate and verify that that is true. I'll teach you that later. But at this moment in time, if you get to 8, you're happy. All right? If you get past 8 or less than 8, then you have to mathematically prove to me that that's okay. But at this moment in time, we'll try to keep them all 8s. Okay? Now, these dots that represent electrons, if you have ones that are unpaired, those are the ones that are going to be the ones available to react in most cases. And so, if I take a look at calcium, how many valence electrons does it have? 2. I would draw something. I would draw it something like this and that. What about carbon? How many valence? 4. So, there, there, and there. And the case for carbon, it looks like I have 4 places to add things. And carbon quite often makes 4 bonds for it to be happy. What about sulfur? 6. 1, 2, 3, 4, 5, 6. How many bonds do you think sulfur would make to be happy? 2. It's got 2 open places, and it would make 2 bonds. The other places are full with the paired electrons. And copper, how many electrons would you assume copper? Now, copper before it has charge. What do we define as being valence? Only the what? Only the S and P's. So the D's we do not deal with, so copper would be 1 and 2. Okay? Now, maybe D electrons get involved, but at this point in time, you wouldn't predict that. You would predict there are 2 electrons that are in the valence for copper at this moment in time. All right, we're heading to making bonds, so we need to talk about this concept of what we're heading towards, a chemical formula. And so chemical formulas are written such that you name every element in the compound, and then you use subscripts to tell you how many are there. And so for water, H2O means I have 2 hydrogens and 1 oxygen. I can draw a molecule that looks like water to show you 1 oxygen and 2 hydrogens. That gives us a little bit more information about what's connected to what. And so hydrogen peroxide, H2O2, carbon monoxide, CO, and carbon monoxide, CO, and they do it twice for some reason. No idea. All right. Now, that's one way that we can do it. What we're going to start to do is this. If I rewrote water, most of the time you're going to see water look like this. I'll write it like that. Or I'll write it like this. This way, quick and dirty, quick and easy, that describes what the molecule that I'm talking about. But if I want to describe the bonds that exist, this is how I would write it, with a line between the hydrogen and the oxygen. A line between 2 atoms represents 2 electrons that are in the bond. Okay? If I wrote hydrogen peroxide, it would look like that. Okay? And so I will actually describe some of these bonds. So that's what we're getting to, is thinking about how these bonds are formed. Now, in the textbook, it can give you all sorts of ways to look at it. And so this right here is CH4. 1 carbon, 4 hydrogens. It can be written as a structural formula, which shows you what's bound to what. Each bond represents 2 electrons. This begins to show you what's its 3-dimensional structure. It shows you a wedge coming out of the plane towards me. Okay, that's interpreted. But I can draw it a different way to show you, that looks 3-dimensional, and that's called a ball and stick model. And this space-filling model is actually the physical volume of each of those atoms bound together, and that probably is the best representation of what it really looks like. But in different ways, you see different, or we highlight different information. And so you're going to see atoms drawn in lots of ways. I will not expect you to draw some of these, until later as I teach you rules how to draw them. But we can represent the bonding of atoms in lots and lots of different ways. And so there are 3 main types of bonding that we classify. All right? This is the force that holds inside, intra the molecule. Okay? The metallic bond, the ionic bond, and a covalent bond. These are the three biggies, the big definitional. Bonds are formed when electrons, what happens between the electrons between those atoms. So something's going to happen to those electrons. All right. I'm going to start with atom A and atom B. And I will draw the Lewis symbols, okay? And what happens when I make a bond, I'm going to give an electron for one and an electron for the other, and we're going to throw them into the middle, okay? Now, when I have two electrons, they tend to like to pair, okay? So I'm going to write them as A contributed 1, B contributed 1. Now, at this moment in time, each one has thrown in an electron, but it didn't let go of its electron. Okay? And so, a tug of war ensues. A will now try to grab both of those electrons, and B will grab both of those electrons and try to pull it. Okay? And then there's a war. Both of them are trying to steal those two pairs of electrons. All right? Now, in a tug of war, a group gets hold on to the rope over here, and a group over here holds on, and they pull, right? The groups are connected by that rope, right? For a period of time. Well, if both atoms are trying to hold on to those two electrons and trying to pull them, the two atoms are connected. Now, they can be equal in their amount of pulls. So the electrons end up being right between them. Okay? Is every person in this room exactly equal in strength? No. Is every element exactly equal in strength of their attraction towards an electron? No. What is the property that an atom wants to attract an electron? What is that property? We named it and gave it a trend. Electronegativity. Fluorine was the most electronegative. Cesium was the least. So, most of the time, you get electrons that aren't shared equally. One is going to be stronger than the other. And then there is going to be a case in which one atom is so strong that it totally rips the electron away from the other atom. But in that case, what happens is B gets more electrons than what it started with. A has less electrons than what it started with. One becomes positive, one becomes negative. Will they stick together? Yes. They will stick together because I now have two charges. All right? They will stick together because the two charges attract. This is called an ionic bond. Up at the top, where the two atoms are sharing electrons, covalent. They share electrons, and the ionic give or take electrons. Now, sharing of electrons, does that mean they share equally? No. In the middle is called what's called polar covalent. Okay. Now I'm going to show you a little symbol. It is the lowercase gamma. Delta. Oh, that looks like an 8. It's lowercase gamma. where this one becomes partially positive. One side is sort of positive, and one side is sort of negative. And so it acts like a magnet inside its bond. And so it has poles, like a north and south pole or a plus and minus pole. That's where the polar term comes from. And so, two extremes. I absolutely share perfectly the two electrons, covalent. And then the other extreme, I totally take away an electron from the other, and one becomes positive, one becomes negative, ionic. These are the black and the white of everything. Okay? Here's the deal, though. In life, is everything absolutely black or white? No. Most things are gray. And in a lot of our bonding, it is a mixture between the two in real life. But what we teach you are the two extremes, because those are the opposites, and a lot of times something's in the middle. Okay? We'll give you rules for when things tend to react like this, and then we'll give you rules for when they tend to be like this. Okay? So ionic bonds form when one atom steals. Now let me use the Lewis symbols to tell you what that really means. For sodium, the number of valence electrons it has is 1. And for chlorine, how many valence? 7. 1, 2, 3, 4, 5, 6, 7. Okay, everything wants to get to octet. Sodium here can get to octet if it gets rid of that electron. Chlorine over here can get to octet if it can get one. And so what happens is that electron gets converted or taken or stolen completely by chlorine, and sodium completely gives it away. I get a positive and a negative, and they snap together like two magnets, and they hold. It's called an electrostatic interaction. Okay, like static cling. Has anybody ever done laundry and that sock gets stuck to your shirt? It's got static cling. This is essentially what's happening. Ionic bonds are typically very, very strong. Those charges really hold those two atoms together. Okay? So that's what actually looks like what's happening. Now, if I think about what's happening in terms of some things I taught you about before, ionization energy and electron affinity. When things react, to give off energy is to become stable. And so it takes energy to take the electron from sodium, and if I give the electron to chlorine, that gives off energy, and so that's part of the reaction. And so one is going to take, one is going to lose, and they get placed into an arrangement called a lattice, meaning that one sodium is next to one chloride, which the chloride is next to a sodium, which is next to a chloride, which is next to a sodium, which is next to a chloride. And it makes this huge array of one after the one after one after one after one. And so when we actually say that a sodium and a chloride get together, that's true. But this sodium has a chloride on this side and a chloride above it and a chloride below it and a chloride on this other side, front and back, as you go throughout the entire structure. And so you get lots and lots of negatives and positives coming together to form that compound. We're going to see that that's where a lot of energy comes out at the end of this chapter. Now, ionic bonds form generally between a metal and a nonmetal, but it can incorporate, and I did show you a sheet, some of those compounds called polyatomic ions. If you have a group that has a charge, it can also be an ionic compound. Covalent bonds. Electrons are shared between two nonmetals, and that's really a good definition. Nonmetals reacting tend to share. The reason is the electron affinity, the electronegativities are about the same. And so one is not strong enough to steal the electron, so they actually have to share because they're just not strong enough to steal one from the other. And so if you take a look, if you have nonmetals bound together, they're usually covalent. They are classified into two types. Polar covalent, meaning unequaled sharing. So this is unequal sharing. And what's called nonpolar or pure covalent, which is equal sharing. So what we usually think about is two nonmetals being bound together. Neither want to lose nor gain electrons, but they share, and when they share, both of them fill their octet or their orbitals. And so we have a bond. An example would be two hydrogens coming together. A polar covalent. Okay, so let's take a look at this. Bromine has 7 valence electrons. For convenience, I'm going to write it in a certain way. Okay? And fluorine has 7 valence electrons. And these two can form a bond. And what you get is what we write is this, but this, that line is equal to 1 electron from each forming a pair. Because one of the electrons came from fluorine and one of the electrons came from bromine, but when they pair together and are shared between the two, then I write a line. This is unequaled sharing because fluorine is more electronegative and bromine is less. And so that means the electrons are closer to fluorine. That means, I just lost what I was doing. Okay, so that means when I make this bonding, colors, lots of colors. When I make this bonding, okay, that means on this side, the electrons are a little bit closer. So this is partially negative, that side. This is partially positive. I can also write it this way, that it tends to look like this. On this side, the bromine, it's kind of positive, and on this side, it's kind of negative. Because it's not equally shared. The electrons are closer to fluorine. On the other case, hydrogen will react this way. One of its electrons, and I make a bond between them. Now, we said everything was happy if we got to an octet. The exception is hydrogen. How many electrons does hydrogen need to get to its closest noble gas? Its closest noble gas is how many? 2. So hydrogen fulfills its octet, or really becomes the noble gas configuration if it has 2 electrons. So hydrogen is happy with 2 around it. Everything else needs at least 8, unless you mathematically prove to me that there's something better. Now, the diatomic molecules are the example of those atoms that are pure covalent. There's not a lot of things that are pure covalent, okay? And so there are 7 diatomic molecules. You just need to memorize them. All right. One other pure covalent is one we do by definition. I will introduce this again, but you should learn it now. A carbon bound to a hydrogen behaves as if it is totally pure covalent, non-polar. And we're going to see this quite a lot. Now, look at this. What does this make? A what? An L, but upside down, or a 7. How many diatomic elements are there? 7. There are 6 of them here, and then oddball hydrogen. Those are the ones that are the diatomics. What is the other element that you need to know in its elemental form isn't just it by itself? Do you remember? Look like a little crown? Sulfur. Sulfur is found as S what? 8. Those are the ones that you should know. In the elemental form, they're not just the element written by itself. It is diatomic, 2 atoms put together is the elemental form, and then S8 is an oddball one. Now, in that sharing of electrons, there's some issues. All right? There's attraction between the nucleus of one and the electron pairs. They like to have electrons. So these nuclei are sharing or attracting to these electrons. But the 2 electrons are both negative, so they're repelling a little bit. And these nuclei, even though they're sharing, there's a little bit of contention because those 2 positives are trying to repel from each other. So the bond that is formed, okay, we might write a line, but the bond is a lot more complicated because of all of these competing. I want to attract, but I want to repel. I want to attract, I want to repel. And you can see that the distribution of where those electrons lie are mainly between, okay, but they also reside around the 2 nuclei, and they hop around all over. But this right in here, it's a little bit more dense. That is what the bond is. The electrons are between those 2 atoms, being pulled on by both of those atoms. So it is a bit more complicated in real life than just a simple little line. Okay. Here I show 2 bonds. This is absolutely pure covalent. There's no imbalance of electrons. Here I show an imbalance where the hydrogen doesn't have as much of the electrons, whereas the fluorine has a lot more of the electrons. And so we can actually calculate how strong the polarity or the imbalance is. We do that by numerically taking the electronegativity value and do a subtraction between the 2. And if the value of subtracting the 2 numbers is around 0, it's pure covalent. If it is around 2-ish, it's in that polar region. And if you get above 3, it is so imbalanced that one actually stole the electron away from the other. Okay, but here's the deal. What we do for this in terms of what we do, diatomics, and carbon hydrogen, pure non-covalent, pure non-polar. These metals and a non-metal. And these 2 non-metals. So, if it's a metal and a non-metal, ionic. Just ionic. If it's 2 other elements, non-metals, it's polar covalent. If it's diatomic or carbon and hydrogen, that's where we get pure nonpolar. That is what we distill it down to. Although we can mathematically calculate them, if you look at a bond, you should be able to identify, does it fit into those 3 categories. What bonding have we not gotten into? Metals. We have gotten into ionic and covalent, the ones we deal with most often. We will then get into metallic bonding next time. All right? Make sure